the steps. From here I go there because of that. What rule, what theorem you're using, and so on. And then you validate if the random number chooses you to validate. Okay. So, what is here the trick? It's from high school. The base is any positive number A. Of course, if the number A is 1, then it becomes boring. The number 1, we exclude the number 1 because it's just boring. 1 to the power, any power is 1. Now, x and y are integers. We know only integers up to now. And from high school, we have this rule, then we have that rule. And then we have that rule, right? Notice something, guys. No. From what I understand, sometimes you are afraid to come to the whiteboard because you might get embarrassed. First, if you study at home a little bit, no problem. You can do something small. You'll get embarrassed if you cannot do anything. But this is not like you're getting married and your spouse disappears. This is great embarrassment, maybe, yeah? Oh. We have to go back to take the cable. You know what? They go to the room, they bring the wrong cable, they take the good cable and put the wrong cable and they disappear. So let's write some rules. A to the power of x, a to the power of y equals, what should I put here, guys? A to the power of x plus y. Now notice that you can use the rule in that direction or in that direction, in both directions, because it's equal sign. And then another rule, a to the power of x, a to the power of y equals a to the power of x minus y. And a to the power of x to the power of y equals a to the power x multiplied by y. X and y here are always integers. For integers, it's easy to prove. All these rules, all these identities, you can call them, rules or identities, just by using. So now, one more rule. A multiplied by B, two different bases now. And brackets, and then to the power of x, where x is integer again. Then this here equals a to the power of x multiplied by b to the power of x. Very often that rule is applied from right to left. Listen. Now, if you remember, we made a contract, right? Because you are 1 minute late and I put your absence. You understand? You cannot be even 1 second late. Vesna, is it okay? No, it's a special contract between me and him. Special contract, only for him. So here, a greater than 0, b greater than 0. These are the bases. Here a, here b. Guys, y why a less than 0 doesn't make sense. Doesn't make sense. Doesn't make sense. Let's see. If a is minus 1. So what can't we do? We cannot do square root of minus 1. So this equals minus 1, if this is the base, to the power of 1 over 2. And this equals to, okay, so the goal is to be able to raise to any power, including 1 over 2, square root. And if we take negative bases, then we cannot do power of 1 over 2, 1 over 4, and so on. That's why it makes sense only the base has to be greater than 0. 0 is trivial, and also 1 is trivial, so we avoid 1 also. But now we don't know these rules if they are valid when x and y are not integers. So here there is a little bit of philosophy. We can skip the philosophy, but if you want to understand, where is that guy at the moment? Huh? He's taking a call. He's taking a call from client. Or maybe second girlfriend. I'm not sure if but during my hypothesis, her eyes became very big. Okay. You can talk. So, we know how to compute a to the power of x when x is an integer. We know a to the power of x means a multiplied by a x time. Now, the main question is, because we want to define a function. So this is a little bit philosophical. We are not going to use it. We're not going to use that philosophy here on that slide too much. But it's good if you, at least one in your life, you're exposed to such philosophy, and you know what is going on in the heart of mathematics. Guys, be careful now, if you want to understand. So the problem is when x is non-integer. Why is that a problem? Because we want to define a function for every x eventually. We want to define a function for every x. Not only integers, but non-integers too. Yeah. It's a new trend, before, I don't know, but recently everybody goes somewhere, returns back. Oh, the homework, yes. So we need to do some work when x is non-integer. So here we will show you two approaches. The first one is elementary one. The elementary one. And there is a second approach. Now, each one can be taken as the base approach. But the second definition of a to the power of x, when x is non-integer, cannot be finished now, because it requires some the second approach requires some deep mathematics, but still we can just introduce the second approach a little bit. Now, the two definitions of a to the power of x, when x is non-integer, of course they are equivalent. We can choose one definition and the other we can prove it as a theorem. And vice versa, we can turn everything around. Now, if we choose one approach as a definition, some statements are easier and others are more difficult, and of course the other one. So this is philosophical, and we will show the two approaches. So, the first definition is elementary, it's easier to understand, to motivate. The second approach is easier to compute. We'll see that actually the second approach is used in every calculator to compute the value of exponential and logarithmic functions. I told you previous time that if you're a business, you're going to use these two functions many times. Sometimes maybe 100 times per day. Alright, so what do we know? We know a to the power of p when p is an integer. What is that? We know that a to the power of p equals a multiplied by a multiplied by a, p times, just here this is an abbreviation, but now we are looking to define for every x here. Guys, what else do we know? We know a to the power of 1 over q, where q is an integer. Try a little bit to understand what is happening with mathematics, why it's useful. Nowadays, mathematics is maybe, I've heard that from 2016, they claim that mathematics is the biggest business in the world. Google is based entirely on mathematical technology. It's called linear algebra. Facebook, I'm not sure, but Bing and Google and the two search engines, they're made entirely on mathematical technology. So what is, and many others, for example, Oracle. Oracle, in the heart of Oracle, is again mathematical algorithms. I had a long list of companies, RSA Dynamics, billions of dollars, and so on. Okay, so what is 1 over q? It's a radical. It's a root q of a. Q is an integer. We understand what it means, root q of a. What is it? Most of the mathematical definitions, they are connected with optimization problems, maximal or minimum. The whole statistic is built on maximum and minimum. So, this here, by definition, this is the maximal x for which x to the power of q is less than or equal a. Let's try square root of 4. What is the maximal a such that x to the power of 2, because here is square root, is less than or equal 4. This is 2. And we get exactly what we know before. Right, so here, this is an integer and this is 1 over integer, so we can multiply them. No, we can use this one. So this is p and this is 1 over q. When we take this, both of them we know what they mean, and then we get here, so let's write a to the power of p, and here 1 over q. Both are well known, and we get a to the power of p over q. P and q are integers. So now from integers, we went here to a power which is a rational number, p over q. When p and q are integers, it's called a rational number. Are there other numbers than the rationals? Yes, many, many, many. Many, for example, square root of 2 is not a rational number. And it's very easy to prove, just 3 or 4 lines. Square root of 2 is not a rational number. So now we need to do some more work. Here is what we can do. When x is not rational, and there are many non-rational numbers, we can define a to the power of x as a limit. So here is a new usage of the limit that we worked before. We take a to the power of y is rational, and this sequence of rationals goes towards x. Now, is it true that for every non-rational numbers, we can make a sequence of y that go towards x, and all of these y's are rational? And the answer to that question is yes. We always have that property. For every x non-rational, there is a sequence of y that are rational, and they go closer and closer to x. So here, pi, we know the number pi. What do we know about the number pi? We know that approximately it equals 3.14. But maybe not everybody knows that the number pi, if you try to represent it as a decimal fraction, it can never be represented as a finite decimal fraction. In other words, the more we continue, we go closer to pi. Pi, there is a mathematical definition which relates the area of the circle with the radius and that number pi. That's the exact definition. But when you try to write it as a decimal number, no decimal number equals the number pi. But we go closer and closer. This one is closer than that. This one is closer than that. So we build a sequence, and all these numbers here, they are rationals. And for rationals, we know how to compute a to a rational power. And we build this sequence, and the limit of that sequence equals a to the power of pi. So now we have a way to represent a to any power, no matter integer or non-integer. Now, what is the problem? With this way, to compute a to the power of pi is a nightmare. It takes very long time. Nobody uses that way. But it's very easy to prove these formulas when x and y are non-integers. So that's one benefit of this approach. Very easy. And all these formulas are easy to prove. So this is, in most elementary courses, this is the definition that they use to a to the power of x when x is any number, not only integer. Now, here's the second approach. The second approach, we start with e to the power of x. What is e? E and pi are the two most famous constants in mathematics. They come in many places in mathematics. So now you take very different areas of mathematics and you open the book and you start looking around, and sooner or later you come to e or you come to the number pi. So when the base is this number pi, this number e is something between 2 and 3. I will talk about that very soon. E to the power of x e to the power of x, we can define it as this infinite sum. At the moment, we don't know what does it mean to compute infinite sums. Now, notice something here. There is a very easy pattern. The easiest pattern is x to the power of n over n factorial. What is n factorial? N factorial? N factorial, by definition, is 1 multiplied by 2 by 3 multiplied by n. Let's give an example. 5 factorial. Take your books and compute how much is 5 factorial. Factorial is a very famous function in mathematics. It's 1 multiplied by 2, by 3, by 4, by 5. And how much do you get? 120. N factorial is extremely fast growing function. Very fast growing function. Do it yourself, don't trust the other people. Compute 5 factorial. 5 factorial is 1 multiplied by 2, multiplied by 3, multiplied by 4, multiplied by 5. No problem. Now, guys, what is 1? 1. Why 1 falls into that pattern? Because 1 is x to the power of 0 over 0 factorial. So this 0 factorial by definition is 1. Why x follows in that pattern? Because it's x to the power of 1 over 1 factorial. 1 factorial is just 1. Now, okay. It was a long conversation, eh? Yes. Wondering who requires such a long conversation. There are only 2 women usually, right? Require such a long conversation. In the life of every man. Right, guys, look here. Look here. If you take some experience, what happens in this infinite sum? In this infinite sum, when you take concrete x and you fix it, and you'll see that as we go along this sum, the terms become smaller and smaller very fast. Very fast. Now the battery is gone, so I don't have the pointer. And it's gone just in the middle of the work, so next time I have to have a reserve. Okay, so this one, the next one is smaller, the next one very small, this one extremely small. Why is that? The reason is that this function here at the bottom, n factorial, grows faster, much faster than that function on the top. So why is this very useful? Because we can cut and we can compute e to the power of x approximately, but still very good approximation. And that's how e to the power of x is computed everywhere. In your laptop, in your phone, in the internet, all of them, they use this infinite sum. But they make, of this infinite sum, they make a finite sum. Okay, now. And here is the definition of the logarithmic function. This is natural logarithm. Logarithm of 1 plus x equals this infinite sum. Now, the top sum has only plus, plus, plus. The bottom sum is alternating. Plus, minus, plus, the next one is minus, and so on. But the bottom sum doesn't have factorials. So because it doesn't have factorials, every term becomes smaller and smaller, but not so fast. But one thing that helps is that the signs alternate. So it goes above, below the true value. And when we cut somewhere, again, we have an approximation for this value, a natural logarithm. So infinite sums, they need to be studied deeper. We are not going to do it in that class. Right. Now, this here has a special base. I don't remember, but 2.7 maybe something is this number. And when we have another number a, any other numbers, we use this formula. Now, why these two are the same, guys? It's actually very easy. And it would be great if you remember it until the rest of your life. It's just a very small trick. Let's see. We need a to the power of x. But we don't know how to compute a to the power of x in the second word. There are two ways to define. And we are talking about the second one. So, we use inverse functions. So we start with the function e, which we know how to compute. And then we put the inverse, ln of a. When we put this, what do we get? E and natural logarithm, they are inverse. We will talk about that in a second. So what is the result of e to the power of natural logarithm? A. We get back to a. We take a, natural logarithm, then exponential, and we go back to a. From here, and then... the butterfly effect. The butterfly effect. You know, you blink, or maybe he blinks, and the moment he blinks, and alright, so now we just need very little. I'm not going even to breathe. Right, so now let's put here x. Let's put here x. And we get exactly a to the power of x. But why this equals that? Very simple. We use this law here. So this equals e, and then we multiply this by this. Now, when you have two numbers, 3 multiplied by 7 equals 7 multiplied by 3. You can change the places of the first and the second. So instead of writing ln of a multiplied by x, we write x multiplied by ln of a. And now we are in business. First, using this here approximation, we can compute ln of a. Then multiplication, and then a to raise to that number, we also have a mechanism. So now we can compute with any base a. That's the idea. Maybe you can remember that trick, it's not so difficult. Everything is based that e and natural logarithm are inverse, so when you apply e to the power of ln of any number, you get back to the same number. You get back to the same number. Okay. Oh, that is an improvement. Now, here, with this approach, we are talking about two approaches. Actually, there are more than two, but let's don't talk about that. So, in the second approach, it's very easy to compute e to the power of x, and very easy to compute logarithm of any number. The problem now is that it's more difficult to prove all these formulas that were written here on the whiteboard from before. Okay. So, exponential functions. Guys, exponential functions for very